Good morning to all of you. My name is Vishal Jayaswal. I am going to take lecture on computer organization and architecture, and today's topic is multiplication. If we talk about the multiplication algorithm for sign magnitude data and the Booth multiplication for sign 2's complement number. Basically, multiplication in computer organization and architecture, multiplication is of two kinds. That is, first one is sign magnitude data and second one is sign 2's complement number. If we talk about the sign magnitude data, then we multiply the magnitude part and we calculate the sign separately, and we only multiply the magnitude part. And if we talk about the Booth multiplication for signed 2's complement number, in which we can multiply with the sign, and then this is an example of two numbers, that is 23 and 19. If we multiply the 23 and 19, we get 437. And this multiplication in the binary form, first we convert 23 into binary, that is 10111, and convert 19 into binary, that is 10011. This is a multiplicand and this is a multiplier. Then we perform simple binary multiplication. Then we can see that basically two concepts are used in multiplication. First one is addition and second one is shifting. For multiplication, we use only shifting and addition, and we perform the multiplication, because here we can see that this is perform the shifting, this also perform the 2 shift operation, and this will perform the 3 shift operation, and this will perform the 4 shift operation. And after the shifting, we can in between we have got the partial product like this, and at last we add all the partial product to form the final output. So we can say that for the multiplication we use only two methods. First one is shifting and second one is addition. First, we talk about the multiplication algorithm for sign magnitude data. The multiplier stored in Q register and its sign in QS. The sequence counter, that is SC, is initially set to a number that is equal to the number of bits in the multiplier. The counter is decremented by 1 after forming each partial product. When the content of the counter reaches to 0, the product will form and process stops. This is the hardware implementation of sign magnitude data, in which we can see that we have a 3 register, that is B register, A register and Q register. The B register has 1 bit register, that is called BS. We can also say that this is a BS, that is act as a flip flop. And A, for register A, AS is a 1 bit register. We can also say it that is a 1 bit flip flop, that is called AS. And Q register also have QS, that is also called as 1 bit register, that is QS. These AS, BS and QS store the sign bit of the number. And B register and Q register, basically B register contains the multiplicand part and Q register contains the multiplier part. Here there is a 1 bit register E, where the supply of 0 is placed to the register E, and this E is going to the register A. And this is a sequence counter. We have to set the sequence counter that is equal to the number of bit in multiplier. So number of bits in multiplier. This is a flow chart of the sign magnitude data, in which we can see that the multiply operation is start and multiplicand is stored in B register and multiplier is stored in Q register. Here these are the calculation of sign bit, that is we place the multiplicand in B register and their sign stored in BS register. Similarly, we store the multiplier in Q register and their sign stored in QS register, and we perform the XOR operation. Then we got the sign of the result that is stored in the AS. There is no requirement of this phase, because we already stored the result in AS 1 bit register, or we can say that 1 bit flip flop. We can set register A, that is clear to 0. Register A is set to be clear to 0, and initially E is clear to 0, and the sequence counter SC is n minus 1, and first there is a single bit check, and we have to check the QN bit. We have to check the QN bit. And what about QN bit? We can say in the Q register, there is a rightmost bit of the Q register. The rightmost bit of the Q register is called the QN. So we have to check the QN single bit. If this bit is 1, we have to perform the A plus B. We have to add A plus B. The content of register A and content of register B has to be added and go into the EA register. And if Qn is equal to 0, if the value of the Qn is 0, then we have to perform the operation SHR EAQ. SHR means logical shift right. We have to perform here logical shift right, that is symbol of SHR, and we perform logical shift right, that is EAQ. We have to logical shift right EAQ simultaneously, and we have to decrement the counter, that is SC tends to SC minus 1. We have to decrement by 1. This is the case of 0, and when the Qn is 1, we have to perform this. Then after we have to perform this also. We have to logical shift right EAQ, then we have to decrement counter by 1, that is SC minus 1. Then after that we have to check the value of SC. If the sequence counter equal to 0, our product is in AQ register. If the sequence counter is not equal to 0, then we have to go to the further step and we have to another check of Qn bit. In this way, we can check Qn bit and then goes into the loop. We have to check sequence counter. If there is a 0, we have got the result. Otherwise, we have to perform this step. This is the example that we can take for this sign magnitude data. The multiplicand value is 23 and multiplier value is 19. Here we don't consider the sign, because in sign magnitude data we can see in the flow chart the sign calculation is already done in this form. QS XOR BS and tends to goes into the AS flip flop. So sign calculation is separated and magnitude data part is separated. So in this example, we doesn't consider the sign and we have used multiplicand 23 and multiplier is 19, and result should be the 437. Next example is show the content of registers EAQ and the sequence counter during the process of multiplication of the two binary numbers, that is 5 times 1 multiplicand and 10101, that is multiplier. The signs are not included. Here our multiplicand is 5 times 1, that is placed in the B register, that is value is 5 times 1 is 31 in decimal, and the multiplier value is 10101, that is placed in the Q register. Here we can set the sequence counter. We have to set the sequence counter, and we have to count the number of bits in multiplier. And if we count the number of bit multiplier, that is 1, 2, 3, 4, 5. So we can see that the number of bit in multiplier is 5. So we can set the sequence counter 5, and we represent 5 in binary form, that is 101. So we set the multiplicand in B register, we set the multiplier in Q register, we set the sequence counter, that is 5, that is 101, and initially if we see the flow chart, A is clear to 0 and E is also clear to 0. So the number of bits in multiplicand, the number of bit in multiplier, that is equal, and the register A number of bits should be equal. So B, that is multiplicand bit, multiplier bit and register A bit should be equal. You have to remember this. So we clear to 0, not single 0. We have to write here, that is 5 times 0, because multiplicand number of bits is 5, multiplier number of bits is 5. So we have to write in A, that is number of bits is 0, that is number of bits 5 and should be 0. And if we talk about the E, initially we have to E clear to 0. So we can write 0 here. So this is the initial step. In this we can set all the values before the multiplication, that is multiplicand, multiplier, sequence counter, register A value and register E value. After that we have to start our multiplication process. First we have to check the value of Qn, and Qn is the rightmost bit of the Q register. The Qn, this is the Qn bit, this is the Qn bit, and this Qn bit is 1. If Qn bit is 1, then we have to add A plus B and places the result in EQ. So here initially the A is 5 times 0 and our B is 5 times 1. We have to add this 5 times 0 and 5 times 1, and we got the result 5 times 1, and there is no carry in this addition. So E is as it is 0, that is initially. So we got the result this. This is a partial product. We can say this is the partial product. After that we can apply the logical shift right EAQ. After adding A plus B and placing the result in EA, we have to perform the logical shift right EAQ. If we perform the logical shift right, we can say that if this bits goes to the right and all the bits, this bit go to the right, this also goes to the right, in this way this bit goes to the right. We have to consider Q also, then we have to shift this also, and this basically this performs on this data. this data, and this value should be discarded. After applying the logical shift right EAQ, this values goes to this here, then here we can place 0. Similarly, in this way, we can shift all the bits in one position right, then we got the 4 times 1 in register A. So, in register A, we got the result 0, 4 times 1. Then, in Q register, this one goes to this position. So, here this 1 is placed, or this one is already placed here, then 0, then 1, then 0, and this one is discarded. This one is discarded. So, we after shifting EAQ, arithmetic logical shift right EAQ, we got this result. We got this result, and we after that we have to decrement the counter by 1. Initially, the sequence counter value set to the 5, then -1. If we have to perform the -1, we got the 4, and write the value 4 in binary, that is 1 0 0. After that, we perform the first step. Basically, this will complete the first step. Here we can decrement the counter by 1, that is 4. After that, we check the sequence counter. The sequence counter value is not equal to 0. Here the sequence counter value is 4. So, we have to go into the loop, and we have to check the value of Qn again. So, we have to check the value of Qn. Here Qn is 0. Take eraser. So, here this is a current Q register, and this bit is called Qn. This is Qn. We have to test this Qn. If Qn is equal to 0, then according to our flow chart, we have to perform logical shift right EAQ. So, we have to remember the flow chart. So, if the Qn equal to 0, then we have to perform the logical shift right EAQ. We need not to add A plus B. Simply logical shift right. If we perform the logical shift right, then here this 0 in first iteration, this 0 goes to the A part. Then the we can see in the hardware implementation, here the 0 is supplied to the E. 0 is supplied to the E. So, here there is a blank space, and that is filled with 0. So, here we can place this 0. And after the logical shift right EAQ, this 0 goes to here, this 0 right shift 1 position, this will also right shift 1 position, and this bit goes to right bit 1 position. This is also shift right, this is also shift right, and this bit also shift right, and this Qn bit, that is discarded. After applying the shift right EAQ, we got this 0 places here. So here we can write 0. This 0 goes to this position. So here we write 0. Similarly, each bit shift one position. So in A we got 0 0 1 1, and in Q this one places here. So we got Q, this is 3 times 0, then 0 1, and sequence counter is decremented by 1, that is here 4, then minus 1 karenge, that is 3. So here the sequence counter is decremented by 1, that is 3. That is right in the binary, that is 0 1 1. So we have to check the sequence counter. The sequence counter is still 3, not equal to 0. So we have to repeat the same operation, and we have to another check of Qn bit, that is equal to 1. We have to test Qn again. So if Qn is 1, then we have to add B. Add B means we have to perform A plus B operation, and our current A is this, and we have to add B, and B is this, that is 5 times 1. So we have to add these two numbers, that is in binary form, and 1 plus 1, that is equal to 0, that is carry 1. 1 plus 1, that is equal to 0, carry 1, and 0 plus 1 is 1. Similarly, 1 plus 1 is 0, 1 carry, and 0 plus 1 is 1. 1 plus 0 is 1, 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 1 carry. After adding A plus B, we can see that there is a 1 carry that is stored in the E register. We have to remember this part. We have to store the carry part in E register. In this addition, we have performed addition and got the carry, that is 1. We have to store the carry in E register. So after adding A plus B, we got the result 1 0 0 1 1 0. So after adding A plus B and place the result in EA register, we have to perform the logical shift right, that is SHR EAQ, and if we perform the SHR EAQ, then this bit goes to the right, each bit goes to the one position right, and this bits goes to the right. Similar, this bits also goes to the right, and this bits goes to the discard. The Qn bit is going to be discard. So after perform logical shift right EAQ, we got the result 0 1 0 0 1 1 0 1 1 1 0, and we have to decrement counter by 1, that is 2. Then we have to test another test, that is sequence counter is equal to 0. No, our sequence counter is not equal to 0, that is 2. So we have to test Qn again, that is 0. If Qn is 0, we have to perform logical shift right EAQ. If we perform the logical shift right, then this 0 goes to this position, this bits goes in right position, 1 bit right position, and this 1 goes to this position. In this way, we have to perform the logical shift right, and this 0 is going to be discard. So after logical shift right EAQ, we got this result, and we after that we have to decrement the counter by 1, that is 2 minus 1, we got the 1, and we have to write 1 in binary form, that is 0 0 1. Then after the sequence counter is not equal to 1, not equal to 0, we have to perform one another steps, and we have to check Qn bit, that is equal to 1. Then if Qn is 1, we have performed add B, and add B means we have to add B in A. And if we add these two numbers, we also got the 1 carry that is placed in the register E, and we got this result. After that, we have to logical shift right EAQ. If we perform the logical shift right, this one goes to this position, and these bits shifted 1 bit in right position. This 0 goes to this position, and these bits also shifted in 1 position right, and this one and this Qn is discard. So after logical shift right, we got the result 1 0 1 0 1 0 1 1, and our sequence counter 1 minus 1, that is equal to 0. If our sequence counter is 0, then we have to stop our process, and our result is in AQ register. So our result is 1 0 1, 3 times 0 1 0 1 1. This is the simple multiplication, that is sign magnitude multiplication. Here we have to follow the flow chart that is given in the slide. Thank you for this lecture.